It's amazing to have Massimo Chiaradia joining us today. So Massimo has been a senior lecturer since 2004 at the Department of Earth Sciences at the University of Geneva, where he's the head of Isotope Tracing Lab. He currently works on the associations among geodynamic setting, petrogenesis of magmas, and the formation of porphyry type deposits at convergent margins. And it's going to be awesome learning from him today about distinct magma evolution process controls, the formation, endowments, and metric ratios of porphyry copper gold deposits in thin and thick arcs. So this is going to be an awesome session. Please keep using the chat and we'll open up the floor at the end. And yes, thank you so much, Massimo, for joining. It's amazing having you.
Yeah, thank you very much, Jess, for the kind invitation. Thanks to Dan for the nice and funny introduction. Good morning or good afternoon to everybody. So today I will talk about some modeling that have been carried out in the last few years, just to try to understand in a quantitative way how porphyry copper deposits form, and especially how can we explain the huge range of metal endowments which are contained in this kind of deposits, with a distinction between thin and thick arcs. So if we look at the map with some of the major porphyry copper gold deposits distributed around the world, we can see, of course, that they are mostly located at either active or past active subduction zones, like along the Andean Cordillera, and others which are, well, of course, are related with past subduction zones, like in the Tethyan Belt. But we find also a lot of deposits here, which one could think that they are associated with the subduction, but indeed in the Southwest Pacific, in most cases, they are associated with a kind of post-collisional. So at the end of a subduction process and in a post-collisional extensional setting. The other thing that we can see is that the different colors indicate different endowments in terms of metals. So the green circles are what I call copper-rich porphyry copper-gold deposits, which are characterized by high copper-gold ratios, which contain more than 10 million tons of copper. So they are supergiant porphyry copper deposits. Whereas the yellow ones are so-called gold-rich porphyry copper-gold deposits, which have low copper to gold ratio, and they have a substantial amount of gold, more than 200 tons. And if we look a bit in detail, like we zoom into two zones, like the Andean Cordillera on one hand and the Southwest Pacific on the other, we can see that the total endowment of these deposits in these two different areas reflect quite well the definition of copper-rich or gold-rich. In the Andean Cordillera, we have a total endowment which results in a gold to copper ratio of around 10 in terms of tons versus million tons. And in the Southwest Pacific, it's around 80, so much higher. So why is it so? Is this there is a reason? Can we find a reason of this? I will try to show you modeling which can explain why we have these differences. And also I will try to come to a model which try to explain why we have within these belts very huge differences in the terms of endowments of single deposits. Okay, yeah, as I was saying before, these are one first thing that we can say is that they are found, these kind of deposits in the Andean Cordillera in a thin subduction, typical Andean setting, whereas these ones are associated most with the post-collisional extension just at the end of a subduction process. So to form a porphyry copper deposit, we need three basic ingredients at least, which are the metals, the fluid which carry them, and the ligands which bind the metals, and eventually also they precipitate them as sulfides. And we know that from a lot of studies, geological, isotopic, geochemical, and so on, geochronological, that the main source of these three ingredients is the magma. Therefore, a lot of effort has been made, especially during the last year, about the concept of magma fertility. So if the magma is fertile, it is a magma which will be able to form a porphyry copper gold deposit. So, but what does it mean, fertility, and what controls fertility? A lot of attention has been given in the last years to the so-called, what I call the intensive variable. So concentration of metals, concentrations of fluids, well, concentration of metals both in magma and in the fluid, concentration of the fluid phase, the contents of the water in the magma, the contents of sulfur, of chlorine, of well, CO2 is a bit more enigmatic, the oxygen fugacity. So all these are intensive parameters in the magma and are for sure very important, as we know, in controlling the metal, the evolution in the magma and in the fluid, and the possible release to form a porphyry deposit. So built on that, there have been created, or there have been, let's say, created a lot of magma fertility indicators, which can be just bulk rock indicators, like a typical one is the strontium-yttrium ratio, which is strongly used both in research and in mineral exploration. With the typical, as shown here, this database of Bob Louts, a typical range for fertile porphyry copper deposits between 50 and 150. A lot of work now is being carried out on zircon fertility indicators, because zircon is a resistant mineral, especially in the porphyry environment, which is affected by a lot of alteration. And also apatite, among others, have been used as fertility indicators. And there are many more, but maybe these three are the most used ones currently. However, not much attention has been given to another variable which may control the size and the fertility of the system. And this is the extensive variable, which is the volume of the system, the volume of the magma in this case, which will control also the volume of the fluid, and mediated by the concentration also the total amount of metal. And this will depend on conditions like pressure, temperature, and time scales. And without quantification, it is impossible to evaluate in which proportion these either intensive or extensive variables, they interact with each other to control at the end the formation in the size of a porphyry copper gold deposit. So what I show here, for example, is a simple example of the interaction between an intensive and an extensive variable. So you can imagine that we can form the same porphyry copper deposit in terms of size, having a small amount of magma with a high copper concentration, or a huge amount of magma with a lower copper concentration. And this applies also to other intensive variables. So we need to know in which kind of scenario we are, because this will change dramatically the processes of formation, and therefore our understanding of the system, and therefore also the application of potential mineral fertility indicators and exploration tools. So what I will try to do today is to try to explain, or to show you a model which try to show the interaction between intensive and extensive variables, and to come up with some indications of what is mostly controlling this. Well, you see here, this is a very simple plot. It is a database from USGS of porphyry copper deposits, which show the relationship between the tonnage in terms of total metal, copper metal, and the tonnage of the ore, with the lines, the isolines here, which are the grades of the systems. So what we can see is that there is a huge 4 orders of magnitude variation, at least, of copper endowments. So what is magma fertility again? We can consider all these porphyry as fertile because they have formed a deposit. But of course, this one, the lowest one in terms of copper contents, and the highest one are differently fertile. And from exploration point of view, of course, one would like to find something at the top right hand of the scale rather than to the bottom left of the scale. So what is controlling this huge difference in terms of endowment? And also, if we look now at copper and gold, as I have anticipated before, this is again just a compilation of different porphyry copper gold deposits in a copper versus gold endowment. We can see that there is like a bimodal or a two family of porphyry copper gold deposits. One which is characterized by extremely high copper gold ratio, or in this case, low gold copper ratios, which is mostly formed in thick arcs and is associated with these green triangles, which indicate association with calc-alkaline magma. And the other family, which is mostly formed in thin arcs, which is characterized by extremely high gold copper ratios and is associated either with calc-alkaline magmas or with alkaline magmas. And as you can see here, the six largest gold-rich porphyry copper deposits are associated indeed with alkaline magma. So this suggests something maybe that alkaline magmas do something with gold, have something to do with gold. So also this kind of dual behavior, we need to explain if we want to understand completely the processes which rule the formation of these deposits. So basically, what I try to put all together is to put all these intensive and extensive variables, intensive like water concentration, ligand concentration, metal concentrations in the magma and in the fluids, composition, oxygen fugacity, as well as the extensive variable, which is the magma and the fluid volume, mediated by the precipitation efficiency to form a deposit of a certain size. And this is overall controlled by the time scales, by geodynamics and tectonics, and crustal architecture. And the outcome of this is what we can call magma fertility. Of course, all this looks quite complicated to put in a model. So to do a model, one always tries to simplify the things and to simplify the parameters to a certain extent. So what is the rationale of my model is quite simple. I start from the end product, which is the ore deposit, and in particular, how much metal can be formed in an ore deposit. And we know that all this metal is precipitated by a fluid, hydrothermal fluid, which is mostly composed of water. And the amount of metal which is precipitated by this fluid depends on the concentration of the metal in the fluid and is mediated by the precipitation efficiency. For instance, we can say that not all the metal which is contained in the fluid is efficiently precipitated and concentrated in one single place to form an ore deposit, but some is lost somewhere. And then we can go a little step backwards, because this fluid and its amount of metal, its concentration, is strictly linked to the magma from which this fluid has exsolved. And the link, it depends on the concentration of the fluid in the magma, which is controlled essentially by pressure and composition of the magma, and is mediated by the partition coefficient, fluid melt, which depends on many other parameters like pressure, like chlorine content in the magma, and so on. And then now we are at the step of the magma, and now the extensive parameters and the extensive variable comes into account. Because we can, of course, produce in the crust different amounts of magma. And how this is controlled? Well, there are several models which have dealt with this and have shown that the productivity of magma in the crust in subduction zones can be modeled by simple thermodynamic constraint, essentially pressure and temperatures, which control the size and the time scale, which control the development and the growth of magma volumes in the crust. And I will discuss this a little bit shortly in the next slide. And all these processes here, they are linked together by the time scale. So they cannot go on forever, but of course they have to go on for what is the time scale of the mineralization. Okay, so all this has to be taken into account. Of course, again, although simplified, is still a relatively complex model. And especially, we have in this model parameters which cannot be constrained with the fixed values, because these values are not known at a precise value. And therefore, we have to consider potential ranges of variability of these values. It's what we call a stochastic approach. And all this model, therefore, is run as a stochastic model, which gives us probability of the process of formation. But this is also good because we can infer from that the processes which have the highest probability to occur. Okay, so I have applied this model to two different scenarios because we have seen that this seemed to be associated with two different kinds of porphyry copper gold deposits. Two thick arcs, which are associated essentially with copper-rich and the largest porphyry copper deposits, and thin arcs, which are associated with gold-rich and the largest gold porphyry copper gold deposits. Although also copper is quite important in these deposits, as we have seen. So the basic difference that we can see here in terms of crustal architecture is, of course, the thickness of the crust. But this different thickness impacts also all what is the transcrustal magmatic system, which feeds the shallow level system, which in the end is associated with the mineralization. In thick arcs, just because of the thickness of the crust and the geothermal gradient, we can develop a very extensive transcrustal magmatic system with a lot of magma, which is ponding at mid to lower crustal level. And because of the high temperature of the lower crust in a thick arc, the magma can grow up to an extensive size. In contrast, in thin arcs, and especially because these are, as we have seen, are associated with many cases with post-collisional extension, this magmatic system in the lower part of the thinner crust is not so extensive, and magma tends to rise more readily to shallower levels. And this has a completely different impact on the magma buildup in the system and on the development of different porphyry deposits, as we will see. Okay, let's start with the thick crust scenario. So this is a parametrization of what is called melt productivity. So the amount of magma that can be produced in the crust in terms of percent versus duration of injection. So what does this mean? In a subduction zone, we know that magma is continuously supplied by the partial melting of the mantle wedge in the form of a basalt. And we can think that in a stochastic way, this magma can be emplaced at any different level in the crust. And for the duration, which depends on how long is going on this process. But we know that in subduction zones, like in the Andes, the process of supply of magma is going on since tens, hundreds of millions of years. So here, what we have done is just to consider this process for a duration of 5 million years. And what we can see is that all these different colors, they indicate the productivity of a melt at a certain depth. The blue is shallow, and going to more the pink colors, it becomes deeper. So what we can see is that at any place in the crust, the productivity, so the amount of magma which is accumulated in a certain part of the crust, increases through time. And it increases much more the deeper we go in the crust. For instance, after 4 million years, we have much more melt accumulated in the lower crust than in the upper crust. And the reason of this is quite simple, is the temperature of the surrounding rocks. So in the upper crust, the rocks are cold, and therefore the injected basalt, which comes from the mantle, cools very rapidly. And it spends a lot of energy to heat and to warm up the surrounding cool rocks before starting to accumulate. And it's always difficult to accumulate because the temperature remains overall quite low. But the deeper we go, the more energy is already present in the crust, because the crust is warm, and therefore the magma doesn't spend so much energy to warm up the rocks, and therefore it can accumulate to a larger amount. And all this is accompanied by also a continuous change in the chemistry of the magma, because the initially formed magmas are, of course, the lowest temperature ones, and we know that the lowest temperature ones are rhyolitic. But if we keep going on and injecting and increasing the volume, because there is more basalt coming in, this mixes with the rhyolite, and therefore the magma becomes always more mafic. When I say mafic, it's not that it becomes a basalt, but it will become a dacite or maximum high silica andesite. Okay, good. So maybe. So now a critical parameter which is important here, just try to switch off the sound. One of the critical parameters which is very important is water. So it's the amount of fluid. The amount of fluid which can be released by a magma, which will, as we have seen before, at the end control the total amount of metal which is precipitated, depends on the pressure, because the solubility of a fluid, as shown here in this example for CO2 in water, strongly depends on pressure. At high pressure, there is more solubility, like the CO2 bubbles in the water before it is open, so it is at higher pressure. Once you release the pressure by opening the cap of the bottle, you decrease the pressure, and there is suddenly exsolution. The same thing happens with water in magma, as shown here. This is a plot of pressure versus, let's say, is excess water, which is nothing else than the solubility of water. So excess water, it means the water that can be exsolved, which is above the line of 0 here, and the water which stays in solution. So we can see that these are simulations for all these magmas that are produced at different levels in the crust. In the upper crust here, all the magmas are water saturated for this kind of initial range of water concentrations, which are typical for our magma. But the deeper we go in the crust, the more we have magmas which are water undersaturated. So they are all below this line. And most of the simulations here, if you see the density of these points, fall indeed below the 0 line. And these magmas are characterized by extremely high water concentration, as shown here. So the water concentrations range between 5 and 20%, with the mode around 12, 13%, which is a huge amount of water, especially if combined with the amount of magma, which can be very high in the lower crust. Another critical parameter that we have to take into account are the metals, and how the metals evolve during magmatic evolution, during magmatic accumulation. And this is shown here in a simple way for copper and gold, of course. Copper is in green, gold is in yellow, and this diagram shows how these metals change during magmatic evolution, which is shown by the magnesium fractionation index. So to the right, we have, of course, more mafic magma, and to the left, more felsic. So these lines are not just drawn like this, they are average lines of thousands of data compiled in the literature. But of course, when we make a model, we try to make an average trend to fit into the to input into the model with a bar of uncertainty. So what is shown here is that in thick arcs, copper continuously decrease with magma fractionation, and gold, it strongly decreases initially already, and it drops down to very low values already at the andesitic composition. So I remind you that the typical magmas which are accumulated in the crust are formed in this range between 4 and 6 weight%, and these are the parental magmas of porphyry deposits. So what we can see is that in a thick crust, these magmas are characterized by lower copper contents in terms with respect to the initial basalt, but still with some copper around 40 to 30 ppm, whereas gold is extremely depleted, is almost to zero. And the difference between these two behaviors is essentially due to the different affinity that copper and gold have for sulfur. So they are both chalcophile elements, but gold is much more chalcophile than copper. And now we know that sulfide saturate quite early in magmas in the thick crust because maybe of the pressure effect. There is a lot of debate, but what is sure, whatever is the reason, is that sulfide saturation occurs early in thick arc magma. And this sulfide saturation results in a strong sequestration of gold and in a less important sequestration of copper. Therefore, there is this dichotomy, let's say, between copper and gold behavior. So if now we run the model, running it for simulations, because I remind you, this is a stochastic approach, so with a lot of potential solutions. This is a typical plot that we obtain. This plot shows the pressure of magma accumulation, so the depth at which the magma accumulates during the continuous injection of magma, and this is the duration of time of injection of the magma into the crust. And the different color codes, each point is a simulation. The different color codes correspond to different potential fertility of the magma. So fluids, in blue, we have fluids associated with this magma that could deliver only up to 1 million tons of copper, and the light blue up to 10 million tons. The green is between 10 and 30, and the pink ones are the most fertile, up to 240 million tons of copper. So of course we can see immediately that the most fertile magmatic systems are those that are formed at depth higher than about 20 kilometers, and after a continuous injection of magma of at least 2.5 million. And indeed, this is quite reasonable because we see this kind of evolution in most porphyry systems. Most porphyry systems form at the end of a multi-million-year cycle, now we know, of magmatic activity. And we have a lot of indications of geochemical indicators like strontium yttrium that these magmas evolve at depth. So if we can put on top of this plot here also some isolines of the volume of the magma, so we can see that the most fertile ones correspond to volumes above 1,000 cubic kilometers of magma. So we need huge volumes to form these, to have these most fertile systems. And this corresponds also to huge amount of water. As you can see, the contour of isolines of water content, they follow quite well the fertility contour, which correspond to the exsolvable amount of copper. And if we put on top of this also the geochemistry model, so the strontium yttrium, this also fits very well with the real observation, because as we can see here, the most fertile systems, they fall exactly in between the 50 to 150 interval of strontium-yttrium ratio that is observed in natural porphyry copper deposits, as we have seen in one of the graphs above. So what is the meaning of this fertility window in terms of strontium-yttrium ratio? These are the same data now plotted in a slightly different way. So we have on the x-axis the strontium-yttrium ratio of the magma from the simulation. And on the y-axis, we have the volume of the magma and the amount of water that can be exsolved from this magma. And we can see that because of the shape of the simulations, the most, in terms of volume, the highest volumetric amounts of magma and the highest amount of magma coincide exactly with this window, which is the fertility window of natural porphyry copper deposits. So strontium-yttrium ratio seen in this way is nothing else than an indicator of a very large and water-rich magmatic system, because this system has evolved at very deep crustal levels and for a long time in order to accumulate a huge amount of magma. How can we test our model now? So we have a model, but can we check if it fits well with the reality? Well, this is shown here. This is of course, we can do this only with those parameters of the model for which we have also data for the porphyry deposits. And one of these potential plots is this strontium-yttrium of the magma versus the total endowment of copper. And what is shown here, the different colors that you have here, ranging from blue to red, are the simulations. And these different colors indicate the density of the points within each cell as a result of the simulations. So basically, the blue part indicates low density points, and the more we go towards the green, yellow, red, and pink, we have higher density, so more probabilities for the solutions of the model. So what is interesting is that now the black dots, which are individual points related to a porphyry deposit, they plot exactly in the same way as the model. So they have a very similar distribution, like this, overlapping with the solutions of the model. I tell you that the color area corresponds to a 50% efficiency. So this is the total efficiency cut by 2, whereas the outer black line indicates 100% efficiency. So there is a lot of space, of room for including deposits like El Teniente or, well, this Rio Blanco is probably now higher, and Chuquicamata and Escondida and so on. So there is room. The interesting thing of this model is that we can think it as a topographic map. So this is a view of the same model translated into a 3-dimensional plot in which we have on the plane here the same variables, strontium-yttrium of the magma and copper endowment, and on the z-axis we have the probability, which is indicated by these different color codes. And here the area is subdivided into three parts: less than 50 for strontium-yttrium, between 50 and 150, and more than 150. So you can imagine to travel along this area in this way, following the red line. And of course, here you don't have any possibility to form large porphyry deposits. Only you start to form a lot of deposits, but with very low copper tonnage. In contrast, if you travel within the area of between 50 and 150 strontium-yttrium, you have some probability, even though low, to form very large deposits. And then the probability to form increasingly lower tonnage deposits increase going down. And if you travel along this path now in the more than 150 strontium values, again you have no chance to find very large deposits, but you have some chance to find smaller size deposits. So this translates into these probability density plots versus copper million tons, in which the different color area indicate the model, and the dashed red line indicated the natural distribution. So we can see that there is quite a good overlap between the natural distribution and the model distribution, with only the area between 50 and 150 showing the possibility to form these large deposits, just because this is the window which corresponds to the buildup of huge amounts of magma and huge amounts of fluids. Another possible way to check the validity of the model is in this diagram. Again, strontium. So these are the strontium related to the deposits are average values of magmatic rocks associated with the mineralizing stage of the deposit. And on the y-axis here, we have the duration of the formation of the deposit. And what we see again is a very good overlap between the simulations and the real deposits. Now the simulations are color-coded for potential endowment in terms of copper at 50% efficiency. And the color codes of the deposits are the same as those of the simulation. So basically, when it's pink, it means that it is a deposit that contains more than 70 million tons, for instance. So we can see that there is quite a good coincidence between the color codes of the simulations and the color codes of the deposit, which suggests that, again, the model is working quite in a correct way. So what is the outcome of all this? Well, we can say two things. Most of the deposits form within this window concerning the strontium composition of the magma, because of the reason that we have seen before. But we can also see that within this window, we can form a huge variation of deposits in terms of their endowment, from very low to very high. So what is controlling this? If we look at this plot, it seems that is the duration of the mineralization. And we can express this in this way, in which I have made a compilation here of the high precision duration of the mineralization of different porphyry deposits versus their tonnage. And there seems to be quite a significant correlation, which corresponds in average to this kind of average rate of deposition of copper in this deposit. So what is the outcome of this? If there is this linear correlation, it seems that all deposits are formed by the same process, which is accumulating copper in average in a similar way in all these deposits. So we can think that the size of the deposits is nothing else but a longer lived process in which copper is deposited in the same rate as in the shorter lived deposit. But only what changes is the availability of fluid, which continuously exsolved to form these deposits and to precipitate copper with the same rate. And this availability of fluid depends on the availability of magma. So basically, if we come back to the plot that we have seen before, this is a very simple plot, but the major difference which controls the different size between the lowest copper endowment here and the highest copper endowment here, as you can see here, is not the grade. The grade is quite narrow. It's one order of magnitude only. Most of the deposits range between 0.5 and 1% in terms of copper grade. But the tonnage of the ore, which means the volume of the altered rock affected by the fluid, this ranges by 4 orders of magnitude. So what controls the different size of this is the size of the system. which is nothing else than the size of the altered rocks. And this alteration comes from the fluid. So there are much more fluids here than here. And why there are more fluids, as we have seen before, because there is, at the end, more magma. So this plot, I think, shows quite nicely that the main control in the different sizes of these deposits is given that the intensive variables are necessary to have fertility, but what controls is that these magmas have probably the same kind of fertile intensive variable, but what changes is the extensive variable, which is the magma size, the volume of the system. Okay, but coming briefly back to the simulation, this is another way to show the simulation. I remind you again, the pink are the most fertile. As we have seen before, at the high depth, in the deep crust, all this huge amount of water and its potentially associated huge amount of copper are in solution because of the high pressure. And of course, if the water stays in the magma and it doesn't come out, it cannot form a porphyry deposit. So this is shown here. The most fertile systems are undersaturated, water undersaturated, because they form at pressure higher than 4 kilobars. But in order to form a deposit, we need to absorb this water. So the conclusion of this model is that, yes, we can have a lot of magma fertile in the lower crust, but in the end, we have to bring it up to form a porphyry deposit. Therefore, we can see that the outcome of this model is that we need a two-stage process in the formation of porphyry deposit. A first stage in which we have a long-lived accumulation of magma in the lower crust, in which fluids and magma volumes build up to a significant extent, in which we also build up copper, even though we lose some copper because of the sulfide fractionation, but still there is enough copper to form huge deposits, because this is compensated by the huge volumes. But then we need to transfer this at a later stage into the upper crust, into the so-called parental magma chamber. And this plot here shows the pressure at which these kind of magmas would reach saturation in water if they rose very quickly towards the surface. And this is the distribution of pressure at which they would saturate. And this shows that there is a range between 12 and 18 kilometers depth, something like this, which coincides very, very well with what we know from petrology, from geophysics, and so on. Therefore, the formation of porphyry deposits in thick arcs is a two-stage process. At first, a long-lived accumulation, which coincides well with the fact that we know that porphyry deposits formed during or preceded by long periods of compression, which favor the accumulation of magmas in the lower crust, and then a release of magma towards the upper crust. And the duration of this release and the efficiency of transfer of these amounts of magma towards the upper crust, in the end, controls the duration of the magmatic hydrothermal life of the systems here, which controls and determines the size of the deposit. So that there is this switch between compression to more near neutral stress conditions which favor the transfer of magma from the lower to the upper crust. It is known already since quite many years. So this is just the size. And we can derive this knowledge also from volcanic systems. So this is a plot showing the efficiency of transfer of magma from the lower crust to the upper crust under different stress conditions. So we have here two extremes. This is a plan view. This is, you can see it like a conduit rising from the lower crust towards the upper crust. We are looking this from the upper crust. And in the case we have a low differential stress, we have these kind of circular conduits which focus very well the magma ascent from a huge area below towards the focused area above. Whereas the more the difference between the two horizontal stresses become larger, the more the magma will be dispersed. And this is shown here, basically. This is motivated by volcanologists, but essentially when you have these kind of conditions, you drain up all a magmatic, a huge volume of magma into a chamber which feeds continuously during a long time what is a stratovolcano. But the more you are in this situation, you will end up with the formation of monogenetic cones. Therefore, of course, this is the situation in which we find porphyry copper gold deposits, just because you focus a lot of magma, and therefore you transfer all these precious amount of huge volumes of copper, of magma and fluids into a focused area, and not in this case. Okay, briefly to end up with the thin arcs. So this is the situation in thin arcs. We have, of course, a crustal architecture, which is quite different. The thickness of the crust is much thinner. And we have this mostly extensional kind of setting, which favors the ascent of more primitive magma directly to the upper crust. So in these conditions, we could expect to have magmas which are more primitive in thin arcs than in thick arcs. Because this is just to show you the complexity, for instance, of the Southwest Pacific, in which we have a lot of microplates which have collided, and the formation of these relatively young to very young deposits are associated exactly with these complex collisional, post-collisional kind of geodynamics. So I was saying that we should expect to have more primitive magmas associated with this kind of porphyry deposits in thin arcs compared to thick arcs. And this is indeed what we can see here. So in yellow, we have the gold-rich deposits associated mostly with thin arcs, and in green, the copper-rich associated with thick arcs. And we can see systematic differences in terms of silica, which tells us that the magmas associated with gold-rich are more primitive in terms of magnesium. They are richer. In terms of iron, they are richer. And in terms of trace element ratios, which indicate the depth, they also indicated that gold-rich porphyry deposits are associated with magmas that evolve at shallower level than in the thick arcs, which is completely understandable because the crust is thinner. But this is a nice validation, let's say, of what we would expect. But the major consequence of this different evolution is on the water solubility. So if we have a relatively undifferentiated magma that rises from the mantle directly to the upper crust, and it starts to fractionate with a certain initial amount of water, it will start to build up water until it will saturate in water. So let's see what is the situation of a magma with a typical, of a basalt with a typical 4% content of water, and what it will happen when it starts to evolve to more differentiated composition. So these curves here in the pressure versus water diagram indicate the maximum solubility of the water for magmas of different compositions. So this light blue is basalt, and the more we go to these colors, the more we go towards the rhyolite. So we can see here that the basalt, when it is at 3 kilobars, it's slightly undersaturated in these conditions, okay? But when it starts to evolve, for instance, to a basaltic andesite, it's already to the right of the maximum solubility, therefore it is already saturated. So it starts to exsolve water. And the more it goes, the more the larger is the distance with respect to its corresponding saturation curve. So it means that it will continuously exsolve more and more water until the huge amount of rhyolite. Okay, so what is the consequence of this is that in these conditions, you have an early saturation of water, an early exsolution of water, which is completely different from the deep crust in the thick arcs, where the water is kept inside the magma. But this has huge consequences in the metal budget. Why? Because if we look now at the distribution, at the evolution of the metals in magmas in thin arcs, in terms of copper, green, and gold, yellow, we can see that in thin arcs, the evolution is quite different than compared to thick arcs. This is an observation. The reason of this, we could discuss it for another hour, but I don't have the time for this. But this you have to take as an observation. These are data, both experimental and real rock data. So what is shown here is that both copper and gold have initially an incompatible behavior. So they increase during differentiation, opposite to what happens in thick arcs, until a certain stage of evolution of the magma when they start to drop. But the thing, if we combine this observation with the depth of the water solubility, in thin arcs, shown here, what happens is that when you start to evolve the melt, you will saturate very early, as we have seen just in the previous slide, the water. So the water will start to come out from the magma very early, when you are still with very high amount of metals in the magma. And this results in a very efficient scavenging of these high amounts of metals into the exsolving water. In contrast, if you go in the thick arcs, this water never exalts. Okay, so you reach magmas in this range of composition for which there is still enough copper, but gold is basically lost. So there is very little copper. So these result in very different behavior of copper and gold in these two systems, with very high gold scavenging in the thin arcs, and basically very, very low gold scavenging in thick arcs. Okay, so this results in the very different gold to copper ratios that we observe in porphyry deposits, either in thin arcs, high gold to copper ratios, or in thick arcs, low gold to copper ratios. And this is shown here by this data with the simulations of the model, which reproduce well the high gold copper ratios in the thin arcs, black dots, whereas we have a much lower both gold copper ratio and also endowment in terms of total amount of gold. And this reflects somehow if we look at very simple grade versus ore tonnage, or total gold tons versus ore tonnage kind of plots, in which we can see that the gold grade is much more variable. It varies by up to 3 orders of magnitude. Whereas if you remember in copper, we have only 1 order of magnitude variation in terms of copper grade. And the major control of the endowments of copper in porphyry copper gold deposits is the size of the deposit. Whereas here, we can see that there is a double control. One is the size, as you can see here, because this is low size and this is high size. But the other one, if you take the same kind of tonnage, there are deposits which are much more fertile because simply they have higher gold grade. And this is probably the result of all the magmatic different history that these deposits have, because these are mostly deposits formed in these thin arcs. Okay, just to summarize then everything, we have seen that in thick arcs, porphyry copper gold deposits are formed by 2 steps. The first step during compression, a long-lived compression, is accumulation of huge amounts of magma in the lower crust, built up of huge amounts of volume of fluids also. We have a partial loss of copper, which doesn't prevent anyway that these systems form the largest porphyry copper deposits on the earth, because this loss of copper is not so substantial and is compensated largely by the huge volume of magma. In contrast, gold is heavily compromised because, as we have seen, is dramatically lost in the sulfide. And therefore, these deposits contain very low amounts of gold compared to copper. It doesn't mean that it's low, because some like deposits like Chuquicamata, they have still around 400 tons of gold, which is not trivial, but it's nothing compared to the amount of copper. In the second step, we have to transfer this to the upper crust, and this occurs during transition to more near neutral stress conditions at the end of this long compression. So I think that the major control in this is tectonic, probably. And the duration and the efficiency of transfer of these volumes, of huge volumes of magma from the lower to the upper crust, at the end controls through a stepwise incremental process the size of the deposit. So the size of the deposit is nothing else, is controlled by for how long this transfer goes on from the lower to the upper crust within the time scales of the deposit formation. And the largest one corresponds to a process which lasts up to 2 million of years, like in El Teniente or in Chuquicamata. In thin arcs, the situation is a bit different, in the sense that we are in a thinner crust, we have a more extensional setting. Therefore, this step here is probably less important, and more primitive magma rise directly to the upper crust. Well, it doesn't mean that it doesn't occur, but is probably less developed in the thick arcs. So these more primitive magmas will saturate early, and they will also take advantage of the fact that magmatic evolution in thin arcs is characterized by completely different behavior of copper and gold. Therefore, they will efficiently scavenge both metals and will result in porphyry copper-gold deposits, which are characterized by high gold-copper ratio. Still, probably we have seen that the amount or the duration of the magmatic activity, so the size of the magmatic system, also controls the size at the end of the deposit. So the different endowments are also controlled to a partial extent by the duration and the incremental buildup of a magmatic hydrothermal system. And with this, I thank you very much for your attention.